To the cloud. Is it recording for everyone?
Yeah.
All right, cool. So yeah, now I'll popcorn to Woodrow.
Hello, everyone. My name is Woodrow Jackson. I am a computer science student at Miracosta College, and I really like computer science. I'm more of into like the software side instead of the hardware side of computer science. And I I guess I'm second year going through my third year. I'm transferring this semester, so I popcorn off to
Thank
Michael.
you, Woodrow. I'm Michael. I'm a Palomar College community college student. My interests are just learning programming and machines. I have a fascination with machines and systems, so my focus right now is cybersecurity, networking engineering, and everything else that it covers. So I'm just fascinated by machines, systems, and how a computer can make its own determination. So that's and trying to learn how to do it too. So all right, that's it.
Thanks, Michael. Thanks, Woodrow. So yeah, just to give you as a preface, we will not, bombard you with like all the math. We'll just like briefly describe what it means, and how we have Python libraries or functions that actually just uh, do all the logistic regression or linear regression models for you. Um, so yeah, let's get started with the agenda. So yeah, we'll first go over an overview of ML, just give you a recap of what like machine learning is and the different problems you'll be encountering. We'll go over supervised learning, which is mainly the main problem we're going to be dealing with in our hands-on technical workshops. Give you a breakdown of like the type of math that is needed, um, the regression problem, the general regression problems, the logistic problems, and as well as designing your ML model to deal with regression and logistic problems. And then we'll end off with a Q&A. So yeah, and then here's the overview of ML, which was introduced in our first workshop. So there's three different problems that you'll be facing when you deal with machine learning. You have supervised learning, which is basically just a training data set that has a set of labeled data. Unsupervised learning, you pretty much have data, but your data is unlabeled. So you have nothing to associate each label or each data in your data set. So for example, if you have like if you have images of dogs and cats and you know it's a dog and cat in the data set, but there's like actually no label to define or describe the data that it is it is a cat or a dog, that's why you would call it unsupervised learning. And reinforcement learning, which is my favorite, it's basically just agents that learn how to interact with the environment. So you can think of robots who try to explore different parts of the room, pick up like a ball, maybe eat food. Guarantee it won't eat food, but opening the door and etc. And this actually, whenever the agent does pick up something, it does receive a reward, which is something that is closely associated to us, like how our human brain system works. And basically, we eat like really good food and we get reward, so we keep eating it again and again. And then once we realize that we're getting fatter, then we get like a negative reward, and then we have to keep working out, and then you get a reward for that. So it's that kind of reinforcement learning is basically trying to model the human brain reward system. Um, so now when you get into machine learning, of course, there is a lot of math needed, and I don't know if most of you guys have learned gone into your math classes and you're just like, what am I going to use this derivative for? When am I going to use linear algebra? What about the partial derivatives? When am I going to use partial derivatives? Well, machine learning is a place to actually use all the math you learned in all your high school classes and college classes. So just to give you a breakdown of what you can expect, the kind of math you would expect in machine learning. So we have three different types of topics. We have linear algebra, which makes up about 40 to 50% of machine learning. We have basic calculus. So whatever you learn in high school, the derivatives, the partial derivatives. Jacobian matrix is also probably something you learned in high school, but also in college. If you forgot about it, that's totally fine. I do have some resources for you guys in the end that you guys can take a look at. And you have to learn the gradients. Now linear algebra, it's basically just understanding like how matrices work, how the matrix to matrix or matrix to vector or scalar to vector operations work, transposing operations. That's pretty important too. It's basically just flipping, exchanging all the values in the row into the columns. And then you have this really advanced topic called principal component analysis, which basically means that you're trying to reduce the dimensions of your data, but also maintain a really um, pretty much maintain the structure of the data so that it still gives you an accurate representation of the model. And then you have probability and statistics. Maybe you guys have taken AP statistics or probability classes, and maybe you're like, when am I going to use this? In general, like people do say, like, oh, what is the probability that I'm going to get a five of hearts in this deck of cards? Well, probability and statistics, or you can say that machine learning is basically um, modeled by statistics and probability. So you have like the correlation, the regression, the measure of center. So basically, the most uh, uh, the measure that you're going to use the most is the mean, standard deviation, and the variance. So we won't go into too much details into all of these topics, but of course, you should do your homework and try to understand these topics if whenever you have time. And this is only if you guys really want to get into machine learning um, because it is really important to when you get into advanced levels like neural networks, which will be described in our next workshop. So now we'll go into supervised learning, which Woodrow will be discussing with you guys.
All right, here we go. So supervised learning. So with supervised learning, the algorithm, the biggest difference between supervised learning and unsupervised, the best way to explain is think of it this way. When your parents are with you, you're supervised, but when your parents are not with you, you're unsupervised. So when it comes to supervised learning and machine learning, we're the ones inputting that data into the table and trying to figure out what we're trying to predict the outcome. So a good example of this would be like if you're trying to figure out how many donuts or how many chocolate donuts are sold during the week, which day is the most common day for chocolate donuts to be sold at. And with that, we'll be using a form of regression to figure out, okay, maybe Mondays or Wednesdays chocolate donuts are sold on that day mostly. But with supervised learning, it's split into two different two different problems. One is classification, one is regression. With classification, we assign test data into specific categories. It recognizes specific entities within the data set and attempts to draw some conclusion. Now with regression, it's we have a dependent and independent variable in which we're trying to look for. And the classic example is the donut shop one, which I just explained, in which we're using that data and trying to figure out, hey, if maybe Mondays or Wednesdays chocolate donuts, people buy chocolate donuts, or even beyond that, what day do does a donut shop get the most visits? So you can also look at that data when you're doing this supervised learning. So these are different ways in which it's utilized. Um, let's see. Uh, Next slide. Oh, regression problems. So problems with regression. Regression is a statistical method used in finance, investing, and other disciplines that attempts to determine the strength and character of a relationship between one dependent variable and a series of other variables. So regression, we can use it to solve many problems besides my little donut problem. Another example would be like trying to figure out where are the most sales in America for umbrellas. It will probably be the places where it rains the most, and you'll probably see a linear regression model of out of the 50 states, which state sells the most umbrellas? Maybe Seattle, Washington, because it rains all the time, or different other areas besides Seattle that rain a lot. So those are different things you'll look at when it comes to regression.
Yeah, and
Next slide.
oh, Woodrow, would you like to explain the math?
No, I
It's okay.
don't.
Just picking on
I'm
you.
not
So
that
yeah.
good at
So yeah,
it.
linear regression. So you guys learned in high school like y equal mx plus b, right? Well, you can sort of see y equal mx b being applied here. So you know in in high school in calculus or it's basic algebra, you learned that b is basically your what we call the bias term. It just translate your graph into like up or down in the y-axis. So that's basically what the bias term means here. Um, and so and theta one, theta two, and theta n, you can think of them as like your m, your pretty much your your slope. But in this case, they're what we call them model parameters. Um, so model parameters are the ones that will be changed up or updated in your machine learning model. So pretty much your model learns from these model parameters given the number of features that you have. So the features you can think of like when you have a data set, right? And we have like a house, like when you're trying to determine the housing prices, you have these different features that you have to take into account. You have like the area, the square feet of the house, the number of houses, the number of rooms in the house. Then you have to take into account like um I guess the nature, like what is around you, what kind of entertainment do you have around you. So those are features that you have to input into your linear regression model, and you try to get your model to update these model parameters and learn from this linear regression model so that it can pretty much output a predicted value. So once you, for example, going back to the housing prices, once your model learns from this data set using this linear regression model, if you want to know the price in like let's say 2021, your y hat will be able to predict that value based on the history it was given. And now when you have like many features, like let's say you have over hundreds of features, now it would be tedious to write y hat equal theta 0 plus theta 1 theta 2 and etc. That's a lot. So an easy way to actually see this representation is through a vectorized form, which you can see from equation 4.2. So y hat is equal to h sub theta with respect to x as a function, and it's equal to theta times x. Now the vectorized form, which we will see in the next slide. This is pretty much how it looks. Um, Now we represent it as a matrix to make it readable for not only just for us to read, but also for the program to read as well. Because any data that you feed into any data that you deal with, and I'm pretty sure some of you guys have been in some data structure classes, everything is just represented by an array or a matrix. And this makes it easier for us to input into our model or into our program, represent it as a matrix and do basic operations like addition, matrix multiplication, um, matrix division, and etc. So it's always good to represent everything in a vectorized form. And you can see that when you read research paper, a lot of researchers that write down the technical details always has everything in vectorized form when they try to like describe data or different parameters in their model. Now, when we program a linear regression model, uh, we're- so when we're gonna program our linear regression model, we're gonna be using sklearn, or what we call scikit-learn. So it's basically just a scientific library that we'll be using to um, fit our data into a linear regression model. So the top right here that says class sklearn, this is grabbed from sklearn's documentation. Basically, this right here will inside the parentheses are the arguments. The only thing we need to take care of is the only thing we need to consider is the fit intercept, the normalization. Pretty much all these values are going to be these are the default values. So when you initialize your linear regression model, you pretty much have to define a variable equal to linear regression, and that's pretty much it. You don't have to put any arguments. It's hard to maybe visualize right now, but we'll show you guys how it works when we show you the code. And the next thing we need to do is when we want to fit our model with the data set, pretty much just have our model learn from our data set. We use the fit function, which is also from sklearn. Now the arguments you need to feed in is the training data and the target values, or what we call the labels. And yes, I will be, yeah, we will, to share, we are recording this. So this will be posted on our YouTube channel. First, we need to figure out how we're gonna post videos that's over 15 minutes long. But yeah, just to continue, the next problem that we will be dealing with is the logistic problem. Now, I, Wikipedia does a great job in explaining what a logistic model is. Basically, it's just a statistical model that is used to output a probability that your output is of a certain class. For example, if you have an image, I love to refer to the image because it's used a lot and it's easy to understand. If you have an image data with the labels cat and dog, and pretty much your whole data set is just cats and dogs, right? Now, if you ever feed in an image of a dog, your logistic model will just compute the probability, actually two separate probabilities, one for the cat and one for the dog. So it computes this probability of where this image is most likely classified as. Is it going to be classified as a dog, or is it going to be classified as a cat? So this is basically just the mathematical representation. And of course, if the math is just too complicated, you can always stop me and ask me questions to for more clarification. But pretty much your logistic regression model is gonna have this form where p hat, the arrow on top of the p hat, it represents predicted value. Once you feed in your model with Once you feed in your data set to a logistic regression model, it'll just output a probability, an estimated probability. And the sigma that you see right here is what we call the logistic function. So, which is represented in equation 414. And all these equations I'm getting all these equations from this book called uh, hands-on machine learning with like scikit-learn and TensorFlow and Keras. And I've actually labeled this. I actually put this free PDF of the book in the resources page. But yeah, so pretty much you feed in your data X. The T represents the transpose. So like what I said, when you transpose your data, it means that you're having all the values in the rows um, go into the column side. So instead of representing all your values in the row, it'll be transferred into the column or represent the column form. So yeah, and logistic regression. So basically, you just feed in your data times the model parameter into t, which is in the sigma in the logistic function. So yeah, this is pretty much how it works. And logistic functions is actually really well used in doing image classification problems. It's also used in deep learning. When you design your own neural network or convolutional neural network, it's heavily used when you want to classify, when you have a data that requires some sort of classification. So yeah, just to give a recap, this model pretty much estimates the probability that instant X or your data belongs to a specific class. So here's a graph, and I know some of you guys are visual learners. So here's a graph. So pretty much when your model outputs a estimated probability, uh, your value will lie between, I don't know, maybe negative. So let's say you have your value that's ranging from -10 to 10, and you want to know and you want to know if your what your input data is lying under this graph. So your output will be between 0 to 1, which will be the probability that your model is like, for example, a dog or a cat. So if you look at equation 415, your logistic regression model prediction will be represented by y hat or this piecewise function. So let's say your dog represents 0 and your cat represents 1. So if your data sees that your cat is, let's say, less than is let's say your cat is 75%, your cat will be given 1 because, or it will be labeled 1 because your estimated probability is greater than 0.5. Now, if it's less than 0.5, then it's most likely going to be a dog. Um, so that's how logistic regression or the model prediction works. Now to actually program it, and again, this I got this from sklearn, and you don't have to worry about what the arguments mean here. It's just to let you know that there are default values that you need to take a look at. I know you don't really have to worry about the arguments too much unless we are like changing some of the arguments. But there's one thing that you need to think about, which is the penalty. Um, the penalty L2, or we call this the L2 norm. Now, when you deal with machine learning, you're gonna come up with this problem called overfitting. Now, overfitting means that your function is too closely fit to your data points. So let's say you have a data and let's say you have a model, and the accuracy for learning or modeling your training data is like 99%. But for some reason your test data set, when your model trains under the test data set, its accuracy goes down to 85%. That's what we call overfitting. It fits too much to the training data set, but doesn't do so well in generalizing to a new set of data points. And that's bad. So what we do is we use this thing called L2 regularization, which you can see at the bottom. Now you can think of W as your weights or your model parameters. You can replace W with theta. And basically what it does is when your coefficients, the coefficients I'm talking about is your theta. In this case, right here, theta. If the coefficient or theta is too high, it'll actually cap it to a smaller value. So that it can avoid the overfitting problem. Now it may not be too obvious or intuitive, but once you go through these problems and you don't like apply any of these regularization problems, you'll see that your model gets worse. Your accuracy actually decreases. But when you do add the regularization, it actually does improve your accuracy. So yeah, we'll be using sklearn to actually program the logistic regression model, and from there we'll be able to see how it does in the end, and we'll get the accuracy value once we train our data set. So yeah, now we'll be designing our machine learning model using Python, NumPy, and sklearn. So just to give you an overview of what we've talked about in our first workshop, these are pretty much the libraries you'll be using throughout this machine learning series. But the main ones you're going to be using is NumPy, Pandas, Matplotlib, and Seaborn, and sklearn in this specific workshop. In the next workshop, when we deal with advanced techniques such as neural networks, we'll be using all of these. That includes PyTorch. So a recap of what these libraries do: NumPy is just a way of analyzing and computing n-dimensional arrays a lot more efficiently and faster. Pandas is just a way to visualize your data and manipulate the data, such as like if you want to remove a feature in that specific data, then you would use Pandas. Matplotlib and Seaborn are just meant to do the basic plotting, and sklearn is just it's just a scientific tool that contains machine learning algorithms such as our linear regression and logistic regression model. So yeah, before we move on to the actual hands-on, does anyone have any questions at the moment? Take some time to like sink all this in and take a deep breath. All right.
Can you do some of this stuff in MATLAB?
Yeah. So, so yeah, most of the stuff can be done in MATLAB, but a lot of people, but you don't see a lot of people actually using MATLAB because one, MATLAB is just too expensive, and three, Python just has a lot more has a lot more libraries compared to MATLAB. Like for example, if you want to train a large neural network, but you want to actually make your model a lot more smaller but more optimal, there's probably going to be a library out there with Python, and there might not be one for MATLAB. But yeah, in general, if you are working for like a company, for a machine learning role, people they actually don't want you to use MATLAB. They want you to use Python and these libraries that we're going to be using.
Got it. Thank you.
Mm-hmm. Does anyone have any other questions? All right, so let's get started with designing our first machine learning, our first machine learning model. So we'll be designing two different machine learning models. One to solve a linear regression model, linear regression problem, and one to solve a logistic problem. Now, like I promised from our first workshop, we will be going through this whole design process where we have to collect our data, prepare our data, train our model on the data, and analyze its accuracy. We won't go through step 5 and step 6. We'll probably go through all the steps except for step 5 in our next workshop. Actually, step 6 is more of like a homework for this workshop. But yeah, deploying the model like through cloud computing tools that will take another workshop in the near future. And one thing I want to note is that if you guys ever have any suggestions or have something that you want to learn, like maybe some specific application like natural language processing or computer vision, definitely send that out into our like Discord channel if you guys are interested in those kind of things. But yeah, so let's go through the design process. Let me. Oh, Woodrow, would you like to share your um, screen, or would you just want me to like share my screen?
I'll share my screen.
Okay.
Give me a moment.
And also, if you guys want to follow along with this code, let me just send it to you guys. But if you guys just want to hand type it and just follow along, we'll just give you the code.
Definitely send the
It
code.
seems like it's not.
Oh, sorry. Sorry, Woodrow. Let me.
It looks like yeah. Okay, let me share screen now. Okay. All right. Here we are.
All right, so I made you guys editors, but do not change. Don't change anything in the code, because I'm not
Don't
sure
be
if
clicking on anything.
yeah, because I'm not sure with viewer if you can actually like edit the code. But yeah, if you as editors, if you guys want to copy this code, you can make a copy of it. But yeah, go ahead, Woodrow. It's all yours.
But
Actually,
okay,
sorry.
so we're gonna.
Oh, sorry. I was about to say, did everyone download the data set?
No.
Okay, let's spend a few minutes then.
Could we put it in the chat, or do they have to go through Kaggle?
They have to go through
Kaggle.
Kaggle to download the data set.
Okay.
So do you guys need help downloading the data set, or are the instructions pretty clear in the Google Doc? Ooh, the Titanic one. Oh, like downloading the data set? Brian. Oh yeah. So let me go through that real quick. Is it okay if I share my screen real quick, Woodrow?
Yeah, let me stop share. Go ahead.
Okay. So for you guys, so the instructions here. So for linear regression, yeah, pretty much you just download. Okay, so let me go through this one since someone needed help with the Titanic. Yeah, so for this one, there's actually only two different types of data sets you need to download: the tests and the train. So I'll download this again just to give you guys a reference on how it's supposed to work. So pretty much go to like any file like downloads. Just download the data set into your local system. So once you have all that downloaded, the next thing you want to do is I'll make a separate. Okay. So pretty much in your Google Drive, once you have all the data sets downloaded, just go to your Google Drive and just create a new folder called datasets. And once you go into your datasets folder, just upload the file that you downloaded. And boom. So once you guys have this downloaded or uploaded in your datasets file, the really cool thing you can do now is when you create your Google Colab file, just go to Google Collaboratory. And in the instructions, I did say that once you downloaded your datasets into your datasets folder, you go to this next step where you have to like make a Google Colab file, call it anything you want, and pretty much copy this code. Now, what this code does is basically just mounts your Google Drive into Google Colab so you can have access to your folders and your files. You run anyways. So Google will it'll take a little while and I'll ask you, okay, so can you get the authorization code, please? So pretty much just click any account that you have. Mine is just going to be NC Bernard. And then you copy your file or copy this code that they gave you and paste it in here. Let me know if I'm going too fast for you guys. So it'll take a little while. It's just authorizing the code, making sure. Now it says mounted at content.drive. So basically now all my files are just mounted now all my files from my Google Drive is mounted to Google Colab. So now I can have access to all my files. So now I go to the datasets folder that I created. For you guys, it may be somewhere different, but here I created a datasets folder. Oh wait, it's still downloading. Crack. Oh, now okay, it's finished. Oh wait, this is the wrong one. Oh, it's in here. I go to my datasets folder, and right here, so I have two different types of datasets, right? So I want to create a train.data, which is going to equal to the file path. Now, when you have the file path, what it means is that your program or Google Colab will look at the file path and find that file in your Google Drive. So you pretty much copy the path, bam, and then you copy your test data. Pretty much just copy the file path again. Shift enter to run the code. And now if you want to see how your data looks like, you just import pandas as PD. And then you do def, which stands for data frame. I'll say data equal to pd.read CSV file. A really nice thing about pandas is that it has its own function for reading CSV files, which stands for comma separated values. Because most of the values you find in CSVs are just pretty much separate by comments. So you read your CSV file and then you read, for example, you read train data. And then once you read your train data, you can use data.head. So data.head means that it'll read the first 5 data points. And there you go. So now you have your data sets. Did that whole process make sense for everyone? Should I go back to a specific process or a step?
No, but you can carry on.
Okay. Cool. So yeah, just let me know if we need to slow down. So you guys can catch up. But yeah, okay, so Woodrow, you can now head into now you can talk about the linear regression model.
Gotcha. I just realized I didn't upload dataset myself.
Oh.
So I'm uploading it.
You just want me to
I'm
should-
uploading to the.
Okay.
I got it.
All right, we'll give you all a
All right.
couple minutes.
All right. Listen. All right.
Oh.
I'm gonna try this again.
Yeah, no worries.
Hopefully it popped in. I just uploaded it, so it should pop in.
Oh, I think I think do drive down mountain again. I'm not sure.
Oh, okay, let me try it again. All right, it seems not. I'm sure I clicked on upload it, but it still hasn't appeared. I think it's best to put it on your screen.
Okay, okay.
All right, so all right, so with the linear regression model, we're going to start with importing the NumPy, the Matplot, the Seaborn, and the Pandas because we're going to use that. Now, from the Google Colab, we want to import the drive. So from the drive, that's going to pop up. So what you want to do is click on the link. Uh, Usually you just paste it back. What they're asking for, you just paste it, and you should be able to work.
Oh, sorry. I lost a linear regression model. Let me give me a little.
It's
Where did I put that? Is it this one? Oh, sorry. I don't even have it on hand. Here, let me get it real quick. Ah, here it is. Okay, no, we're good. We're
uh,
good. We're good.
yeah, that's a lot of time.
We're good.
I'm just reading the comments at the bottom. All right, there we go.
I gotta do this again. Yes, I do have a lot of tabs. I actually have 5 browsers that are pretty much similar to how many tabs I have right now.
At that
Okay.
RAM life.
I have enough RAM to handle all this. Actually, Brave is just a really good browser. It uses less RAM. All right, but continue on, Woodrow.
All right. So now that the Google Drive mount is mounted, so then we use a different we're using different versions. We're using a version of NumPy, Matplot, Seaborn, and Pandas. And then we're mounting the drive as well. Again, now we're getting into the data set. Now, if we look at the data set, it's going through our Google Drive, and by that we're using a shared drive, which is giving us the destination where the .csv file is. So wherever the destination of the CSV file, you want to copy the address of it and place it into the data set right there. Now from that data set, you're going to read it. And so you see the pd.read underscore CSV. From that, we're reading it into data. So now that is the data, we're going to use head. Now with the head, it just gives you the first 5 of the data you're looking for. So it's going to give you the top 5 of from the zero, like when you program, you always start at the zero array. So there's always 0, 1, 2, 3, and 4. So that's why you see the 0 and it counts to 4 instead of 1, 2, 5. Because when it comes to computer programming, you're always going to use you're always going to start with 0 before you count. I know it's weird, but we always start with 1 normally when we count to 5. We don't say 0 then 5, but with computer programming it's always 0 to 5, but it's going to be 0 to 4, which is pretty much 5. Now from there, we're going to move down a little bit. All
Oh,
right, so the data set contains several features. Oh,
it's okay if I describe the data
you
set real quick.
go for it.
Yeah. So when you guys go into Kaggle, it's always important to understand the type of data you're working with. And so yeah, I mean, this data set is just basically just um uh pretty much our task is to output a value or the probability that a student or a college student from India will get into the master program in the US. So there's a few parameters included in here, but yeah, I just want to point out that always read the data and try to understand the data as much as possible, and that's what we'll be doing in this workshop. But continue, Woodrow.
Okay, gotcha. So what the data we're using is the GRE scores, and we're using emissions. So this data is I don't think I explained it, but the data we're using is the emissions predict, and we're just predicting the scores and everything of how, if you were to apply for maybe for a master's program at a university, what are pretty much the criteria of you being accepted into it. So this will predict your score if it's a certain level, or if your statement of purpose or your letter of recommendation or your GPA is going to determine what is your possibilities of getting into that university. So as we go down, now right here we have a data describe. With data describe, it's giving us the count of everything, the mean, the SCD, and the minimum. So it gives us the count, the mean, 25%, the 50%, and the 75%. Nathan, could you help me with this one? This
Oh
one's
yeah.
a little
So the description
toughy.
of the yeah, the description of the data, basically what the count means is that it's just giving you the maximum or the maximum number of data points or samples inside your data set. So in this case, we have a total of 400 data points, and each feature or so the features is basically the parameters we have, right? We have the GRE scores, the TOEFL scores, the statement of purpose. We have 7 different parameters. We have 7 different parameters, and we're all taking all these features into account when we train our model. So all these features will determine like your probability of getting into the university or the master's program in the US. So yeah, the count means we have 400 serial numbers, 400 GRE scores, pretty much just 400 students in this data set. The mean basically just gives you the average value in each of these features. So for the GRE score, the average value is 316. For the university rating, your pretty much the university rating is like how much you are, how prestigious is your university basically. And so if the mean value is like 3.08, and the CGPA in India it's actually out of 10 instead of out of 5, I think, or out of 4 for the US. For them it's out of 10, and the average GPA is 8.5, and etc. Another thing to consider is that when we do deal with when we do train our model to actually predict a value or probability, we are actually going to be using the chance of admission. Um, so the chance of admission is basically just going to give us our labels, and we're going to be using those labels um, to associate our data or all the features into this probability. Um, So yeah, hopefully that makes sense for everyone. If that doesn't, I'll be in the chat keeping track of like your questions. But yeah, um,
All right. All right, so now we're looking at the null values, and null data, it just gives us the values of what numbers are null. So the serial numbers, GRE, everything that's a zero is gonna pop up. So the data.drop serial number access columns, for that one, it's just dropping. If you notice, scroll up a little bit, with that one, I'm gonna have to have you scroll up and down. So as you notice, there's a serial number in the counts, but when you do the data.drop, it takes off the serial numbers. So now you just have the GRE score, university ratings, the SOP, the LOR, and the GPA, and the research, and the chance of the admissions. So by doing a data.drop, you're labeling, hey, we want this serial number column gone, and you say the axis of that column is gone. But if you're saying, you can change it up too, and you can say we want the row gone, and you just take out the whole row as well. Going down, visualize data. So slowly go down. So we have the SNS and plot of the GRE score and the GPA. So this is a linear regression model of of a comparison of the GPA score and a GRE score, and we can see it as and you can see the straight line going through as higher as it goes. Okay, yeah,
Oh,
that's right.
yes. Oh, can I also
Oh wait,
add?
that's you, Navy.
Yeah, can I also add to
Go
something?
for it.
So this line right here that you guys see, it's basically just like um it just shows the relationship between like the GRE score and the CGPA. So you can pretty much see that the higher your GPA, you can pretty much see that the students who got a higher GRE score also has a high GPA. So that's how you should be analyzing the data. You have to find the relationship between many different features that you think are really important when we train our models. So that's what the line is. It basically found a relationship between all the data points, or pretty much the best fit line, um, that describes the relationship between the GRE score and the GPA. But yeah, continue, Woodrow.
Okay. Go down to the second model, and this time we're using GPA and chance of admit. With this model, we're seeing, whoa, uh, yeah,
Oh, I
I
can
don't
describe.
know anything about this
Yeah,
one.
so sorry. This one's actually a
Yeah,
faulty one
describe that one.
because this one's a faulty one because there's actually supposed to be a high density of color. Now if you actually get the now if you actually if this is plotted really well, you'll see a high density of color or a darker color here, which just shows that um with people with higher GPA has a higher chance of getting admitted. That's what it really means. So when you guys do some sort of plot like this, make sure to have the color or the density of the color shown in here. I was trying to figure it out, but uh, I forgot to take this one out. But yeah, that's what it basically means.
Definitely made me freeze. I was like, wait, I'd never seen a linear regression model like that. It looks like a fingerprint to me. All right, so moving down, we go to GPA and the TOEFL score. So we can see the relation of the GPA score and how do you pronounce that? I keep saying TOEFL score.
Yeah, you can say
I know that's a different score.
or TOEFL. Oh, you can say TOEFL.
All TOEFL.
Yeah, you can say that.
I'm just gonna say TOEFL. So we can see in the TOEFL and the GPA that the higher the GPA and is also going to be higher the TOEFL as well in relation. And moving down as well, we can see different graphs as well when using our linear regression. Slowly go down more, some more. All right, right there. So with the GRE score and the chance of miss. Oh, oh, okay. So the SKL learn model and the SK and train set linear regression. So with this, we're doing never data drop. So we're taking a chance of a minute and we're dropping that data. And then we're going to say, hey, we're going to try to test it out. So now we're developing a test model with it by using linear regression. And with that, we're also fitting the X train and the Y train into it. And slowly go down. Oh wait, are we at the bottom? There we go.
Yes, we are at the
Yep.
bottom.
With that, we're using to get the CV scores, we're using linear regression. And from that, we're getting the CV mean and the STD. And through that, that's how we would train the model itself. You want to add anything, Nathan?
Oh yeah, so um oh yeah, so just to go back, we only dropping the chance of admission because our training data doesn't need this, but we're actually using the chance of admission as our labels. Um so we're using this as our labels, and then we're actually splitting the data set into four different types: our X train, our X tests, our Y train, and our Y tests. And luckily, sklearn has a function called train test split, which pretty much splits your X data and your Y data into 4 different types of data for you. And so it makes it easier for you to for it makes it easier for the researchers to do actual testing. Now when you do now this is something important too when you split your data. It may seem trivial, but it's actually really important. When you like for example, when you go through neural networks, it's actually important to split your data into a training set, a training set, a testing set, and a validation set. But the validation set is something we'll discuss later on. But basically, usually the good number to split your data is 80-20. So 80% should be training, and your 20% should be testing. I'm not sure what sklearn does here. I think it does it 50-50 in this case, but usually the train test split has a function or another argument where you can specify how much percentage should be distributed to the training and the test set. So yeah, that's something to consider. Now, the linear regression, you're pretty much just defining your or you're pretty much just defining your linear regression model. sklearn right here. We already defined it from the sklearn linear model. So this is the linear model is basically just all the all the linear regression models that you would find in this specific library. But another important concept that is also important, and it's actually really important when you have a limited amount of data, is the cross validation score, which I will show you what it means. So here it is. So cross validation, basically just a resampling procedure that is used to train your machine learning models when you have a limited amount of data. And there's just this parameter called K. We call this a K cross validation. But yeah, the K refers to the number of groups that you would want to split up your data into. So in this case, if you have K equal 5, you're pretty much splitting your data set into uh, five different groups, or what they call folds. And pretty much what it does is that your machine learning model will go through all these different types of splits. So it'll go through first, if it goes to, so if your machine learning goes into the first split, it'll first train it'll use all that training data in fold 2, fold 3, fold 4, and fold 5. The machine learning model will actually learn the training data set, and then it will train itself with the test data set and output a metric, basically the accuracy. So it'll keep doing that through all the different types of splits. It'll output a metric, or in this case, an accuracy value. For example, if let's say our metric 1 is like 90%, split 2 is like 95%, and etc. above 90%, then you take the mean of all those metrics and you pretty much divide it by 5, and then you get the average accuracy value. So in that case, it could be more than 90%. And this is just meant to make sure that your model doesn't overfit. And like what I said before, overfitting means that your model is just fitting to the data too closely. So meaning it could do super well and understand your training data really well, but it'll do so bad in your test data set. Meaning, let's say you have 95% in your training data set, but it has like 85% in the test data set. That's bad. That's what we call overfitting. But yeah, like what Woodrow said, pretty much it just outputs a mean and a standard deviation. So how far is the values separated from each other? How much variance is within the data? But what we really care about is the mean, because the mean is what gives us the accuracy of our model. So in this case, the cross val score, which is given by sklearn, you pretty much input your linear regression model, your training, and your training data set. CV stands for the K folds, or the K parameter. So we want 5 folds, 5 folds, my bad. And scoring, basically it's just R2. R2 is just, won't go into too much detail, but R2 is just a way to measure your predicted value from the true label itself. So it'll provide you like a relationship or the accuracy between all the data points with the labels. So yeah, over here we tested, we fitted our model with our testing data set after we trained our model, and we got like 78%, which is not so bad, right? Better than just predicting out of like, making prediction out of chance, right? So 78%, that's okay. That's pretty good. And now when you guys do test this out, you can pretty much input different types of values into your model. So like what we said, so we have three different parameters that we were considering. We have, let me see if I can. Yes, we have the GRE score, the TOEFL score, university rating, SOP, that is what did SOP stand for again? Ah, your letter of recommendation straight, your statement of purpose, your GPA, and etc. So you have all these parameters. Now, if you want to test if you want to test your model with different values, then you could pretty much input your values into here. So in this case, I have 305, but let's say I have a higher GRE score. Let's say I have 337. Oh, oh, that's right. I didn't even define my model. Oh, that's what I forgot to do. Hold up. I forgot to run everything while. Okay, so this should run everything. See our CV value change, but that's okay. Usually it's just our data points are just randomized when we do the cross validation score. So it can do better in some cases or do worse in some cases. But over here we tested our model, got 78%. And now when we test our model with different values, we get 75.5%. Now let's say I do have a 337 GRE score and I also have research experience. I have a 79.4 chance of getting in. Now let's say I have my GRE score is 200. I have a chance of 53.3% of getting into this university. So yeah, that's like the power of machine learning. It's able to predict. It's able to make a good prediction with different test values that's not really in the training data set. In general, it's actually really hard to have a good generalize to make a model that generalizes really well into the real world. And there's actually a really specific topic we will discuss later on, but after this workshop. But yeah, so that's pretty much it for this linear regression example. Woodrow, did you have anything else that you would like to talk about? Oh, you're muted, by the way.
Yeah, I was talking. I was like trying to talk. And I was like, wait, I'm muted again.
No
But
worries.
no, you pretty much covered the parts that I missed. So it's yeah. Does the real question is, does anyone else have any questions of what else could you use linear regression for, or how we could use it to benefit society or something?
Yeah. Does anyone have like any questions about the technical details?
I think
All
that
right.
sounds as a no.
All right, cool. So now you may be sitting here and like, okay, so I'm like an electrical engineer. I'm computer science, but I want to get into robotics. I want to build autonomous cars, computer vision, make robots like move on its own. Why the hell are we dealing with these types of data sets that are more financial or doesn't really not really applicable to to the real world? Well, even though it is technically related to the real world, how is it benefiting like how's it benefiting the community? Well, yes, you guys are electrical engineers. You guys are learning about like robotics and airplanes and autonomous like drones, but it's always important to actually understand the foundation of machine learning before you actually get into robotics and autonomous systems when you like build your own machine learning model to do object detection, right? It's always important to understand how to pre-process your data and go through this whole process. Um, so don't worry. In the near future, we're actually in our next workshop, we're actually going to do a little bit more something specific that's pretty much related to digital signal processing, which is pretty much image classification, um, or computer vision in general. So we'll go into that. But yeah, now the next thing that's going to be really important to understand, and this is something that you need to understand really well before you get into neural networks, specifically, especially when we do image classification, is logistic regression. So going back to our slides, what we talked about. Now, logistic regression is basically just estimating a class of probability that your this specific input is in this specific class, right? Like the image example, right? Is the input image you gave me is a dog or a cat? Now logistic regression is um or what we call okay, yes. So logistic regression is also important in neural networks when you're trying to classify a class of probabilities for doing image segmentation. So basically what image segmentation looks like, and this is something that a lot of companies like Waymo, you guys never heard of Waymo, or Tesla, this is what the autonomous or the autopilot uses when it controls like the cameras. Pretty much just sections or tries to um, it looks into the whole image, and if it sees a similar, like if it sees objects that fall under a specific class, for example, if you see a bunch of persons, if you see a bunch of humans that fall under person, then it'll classify it as a person and or a human, and it'll color it red. And of course, like with cars, if you see cars that, or it will fall under the class of vehicles. If you see vehicles, it'll classify as blue. This is used a lot in autonomous systems or autonomous vehicles. If that's something you guys want to get into, object detection is okay too, but image segmentation happens to be a little bit more better. So let's get into the basics. So I have two different examples here actually. So I have a basic logistic regression, and then I have another one with Titanic. Now Titanic is actually a little bit more complicated, but I'll have you guys look into it more. But in this workshop, we'll skim through it. But we'll start off with a really simple example. Now, for this data set that we're dealing with, we're doing a student pass fail data. So if you guys want to download this data set, under the instructions, I did put a link to that data set. Pretty much what you need to do is just like download the zip file. Just download the zip file, put it in your documents or whatever, unzip it, and just upload it into your folder. So in this case, I have my, let me run my code real quick. In this case, I have my data set under this folder right here. Second workshop. Yes. Wait, no. Data sets right here. The student pass. So basically, just like what I said, just copy the file, just copy the path. Copy the path, put it into your dataset variable, and just upload it. So basically, what this dataset, basically an overview of this dataset, it has three different features. It has a self-study daily, meaning how many hours do you study a day, and then it has a tuition monthly, which is basically just the amount of tuition you pay monthly. And I think this is in, hopefully not in thousands. Or maybe it is. I think this is how much money you spend monthly, and then you get a pass or fail. Like, did this student fail or pass this quarter? So if I run this code cell, I'll just print the first 5 points. Now, if I want the first 10 points, I'll just run the first 10 points. But another thing you could do is actually, if you want to read the tail or the last 5 points of your data set, you could just do df.tail, and I'll just read the last 5 data points in your data set. Now, there's one important thing that we want. Now we need to pre-process our data, right? We need to split our data into features that we think would be beneficial for us. So in this case, our X training data set, we don't want the pass or fail. The pass or fail is basically our labels. We need these labels to associate our data with some labels so that our model understands that if I have this set of specific features, then this should be the specific label. So drop it. It'll be pass or fail. and then I set y to equal to the pass or fail column. Right. So now, like what we did earlier, we want to split our data into a training and a testing set. So we split our data set into x. We input the x and y arguments, which is our data, our data sets, and the random state equal 4 means that you're just randomizing or shuffling your data samples. So it's actually really nice to. It's actually best practice to shuffle your data every time you train your model because it tries to learn from a set of data points, but at a different, in a different position or space, or a different um, part of the data sample or a different location in the data set. So when you shuffle your data, it actually just has to relearn everything. It has to strengthen its model, its coefficients, or the model parameters, I would say. Um, so yeah, it's always good to do that. And like what we did in our previous example, we want to define our logistic regression. So using sklearn, they already have a function for you that uses logistic regression, as shown right here. And it's pretty simple, right? So we define it and then we use the logistic regression.fit. So we fit our X training data set and our Y training data set into our logistic regression model. And then from there, once you fit that model or fit our data set into the model, it'll output your theta values. And so once it outputs your theta values, then you can find the prediction. You can find your Y pred, or in mathematical representation called Y hat. We now predict our now we try to predict our model that we use to train our training data set into with our X test data set now. So using our logistic regression model, we predict the X training data set, and then we get the accuracy of the model. So using sklearn again, they have a specific they have a specific function called metrics. So metrics has another function called accuracy score. So it'll pretty much compute the accuracy of the Y test and the Y prediction. So the Y prediction is basically the Y labels that we got from our logistic regression model, and then our Y test is basically the data that we have. Oh, sorry, the Y test is basically the specific the labels that we want. So in this case, we have. So let's say our Y test is basically equal to 1 or 0, right? So basically, in order to test the accuracy score, we pretty much have to do Y test minus the Y prediction. So you get your actual value that you wanted, and then you subtract it with the predicted value they got from your model. And then from there, we can calculate the accuracy percentage, and bam, we got 96.8. So if you want to, test your model, you can do your just grab your logistic regression, use the prediction function. And now NP array, we didn't discuss NumPy yet, but basically you can create an array using np.array. And what we're trying to do, and we created a 1 to 2 dimensional array, which is 4 and 38. Now, what 4 represents in this case is the amount of hours I did, the amount of hours I put into studying, and the amount of money I spent that month for my tuition. What reshape does is actually just reshapes your matrix. So if we were to, let's say we have this. Let me just delete this. And now let's say my first friend is, now we want to know the shape of my model, or of this matrix. First friend dot shape. Wait a second. Oh, sorry. My np.array dot 4 and 38 dot shape. Did I not? Oh, I see. Let me define this x value first. And then I will print the x dots. What the? Oh, wait. Oh, I see. What is? Can I just? Okay, so as you can see, our our data is pretty much 2 by 1. Now if we want to reshape our data, we just do x dot reshape. X dot reshape. Oh, what is this? Oh, wait. Oh, I see. Dot shape. So pretty much it prints out the. So basically, our x shape was 2 by nothing, right? But now when we reshape it, we pretty much we try to reshape it in a way that it is able to be we pretty much reshape it in a way where it is readable for the program to read. Because if you don't reshape your models at times or your matrix, you'll get a lot of errors, meaning errors such as, oh, this matrix doesn't cast onto this matrix, or this matrix cannot be multiplied with this matrix because the shapes are different. So usually we do reshape our matrices at times, and we'll go into more details about this, but we reshape it multiple times or at times to make sure that the matrix operations um, will succeed in such a way that it doesn't get the error, oh, these matrices don't have the same shape. So we'll get into the detail later on in the future. But in this case, we define our first friend, and we get a probability of what the heck? Oh, dot reshape. I think this works now. Wait a second. Before using the estimator. Oh, that's why I did wrong. I defined x differently. There we go. So now my first friend, our first friend here our first friend here failed. So yeah, so if you're putting in 4 hours of just studying and only $38 into your monthly tuition, then you're gonna fail the class. But your second friend here happens to put 8 hours of studying and puts $29 into his monthly, like maybe for spending food or spending money on his food. This guy right here passed. He passed the class, right? So that's good. So that is just a simple logistic problem that that we have just developed here. But in general, it's not as simple as that. Now, before I move on to the other example, which is the Titanic dataset, does anyone have any questions so far? Is there any confusions? Anything that didn't make sense at all?
What was the X that you changed? That was the problem.
Oh yeah, so this X right here that I defined, which is basically my training data set. When I was doing the example, I did X equal np.array. Now, it pretty much when I did this, it overwrote my current X value that I had. So instead of X equal to my data set that I have here, the program actually overwrote that value and converted it into an array, or replace it with my MP with my array that I made here. So yeah, always make sure that when you try to make sure that when you try to do like maybe examples or try to do some testing, make sure that you don't overwrite your values. Does that make sense?
It does.
All right, awesome. Any other questions? All right. So, now this basic regression model, which I will send out to you guys right now, it's very simple. It's okay if it didn't make sense. If it doesn't make sense, just always ask me questions, and also you can always ask me questions, or any of us in the Discord channel. But let me show you guys this link. I will also post the Google the Google Colabs in the Discord channel later on after this workshop. But yes, now remember what I said. It's not as simple as it. Doing this sort of logistic problem, the simple one, it's not really common. Like when you deal with data sets, you're most likely going to be getting a data set that contains a lot of features. You have to do a lot of data pre-processing. You have to find the features that are most important for you to train your model. You have to find some correlation between these different features. In this case, um, how does the self-studying, how does putting amount of this amount of hours of studying daily, and this amount of money in your and this amount of money, all right. Oh, sorry. So how are these two features, specifically the amount of hours you put into studying and the amount of money you spend monthly, correlate with each other? How does it? What kind of correlation or pattern can I get in order to know if I'm going to pass or fail? Now, this is a simple data set, right? Now, let's move on with the logistic regression data set. And let me show you guys this data or this Google Colab. Ah, just so you guys can follow along. All right. We don't need this. All right, so there's actually a lot more going on in this program. So again, let's import our necessary packages. Now, I won't go and if I'm going too fast, please stop me. So import your necessary packages, your NumPy, Matplotlib, Seaborn, sklearn, etc. Know what version you're working with. It's always important to know what version you're working with because sometimes um, some of the newest versions will deprecate the functions from previous versions, which is a big no-no. It's really hard when it's really hard to know what kind of error you're having, and then you realize, oh my gosh, it was because of the version I was working with. So it's always good to know what versions you're working with. Again, your Google Drive. You always have to do this whenever you're reopening your notebook. And bam. Also, I know I'm going a little bit over time. This workshop is meant to last for about like an hour and a half, but yeah, just let me go through this data set real quick because this is something I want you guys to take a look at and test out for yourself. But yeah, I have two different types of data sets. I'm working with a training data set and a test data set. And in here, I'm combining the training and test data set because we want to keep track of. We pretty much just want to have all of our data set combined in one matrix. And of course, like what I said again, you want to analyze your data so that you know what you're working with, you know what parameters you're working with, what each parameter, what does the features mean, and etc. So in this case, we're working with a Titanic data set, meaning we're trying to predict based on these parameters that we have, which is the survival probability, the P class, which is like the tick class you're in, your sex, your age, the number of siblings or spouses you have on board, the number of parents you had on board, the fare. So what was the price of each how much money did the passenger need to pay, the cabin number, and where did the people embark from. So in this case, our task is to pretty much predict whether this person survived the Titanic crash or not. Because in this data set, it only about 38% of the people survived the Titanic crash because there was a limited amount of boats. But we're trying to figure out how many people. We're trying to predict whether this person survived or not, and the values you're gonna get is gonna be 0 or 1. And you can see from here our data head. We have passenger ID. We have the survived, pretty much the people who survived. So passenger ID 2, namely Cummings, Mrs. John Bradley. They pretty much survived. And of course, you can get the last 10 data points that you want from this specific data set. So, like what we said, we want to collect our data. Now, the next step we want to do is prepare our data. So, preparing our data means, again, we want to take out take out any columns or features that may be useless to us. But before we do that, we need to know what is the correlation between all these features? Is there a correlation between the age you are is there a correlation between the age that you are? Wait, is there a correlation between the sex and the age that would predict your survival rates, or is there a correlation between the amount of money spent as well as the number of siblings you had on board? Is there a correlation between those two features that would help you predict the person's survival rate? So before we go into that, let's try to see what our data has for us. Let's describe it. So we know we have about a total of 891 data points. Now, their survival rate that we see right here is 38%. The average age is about 29 years old. Some people had doesn't make sense to have 0.5 siblings. But the average fare was about $32, right? That's all we need to know for this. Now, if you guys want to go into a lot of detail into what the survival rate was between the P class, which is your ticket class. There's three different types of ticket class, 1, 2, and 3, and your survival rates. So what I did here is that I got my training data of these two specific columns, and I group it by the P class. So this will be in the first column. And I calculate the mean of these values, and I sort the values by the survival rate. So the mean is basically just like, of course, gather all your data points, add up all the values, and divide it by the same length of data points that you calculated with. So in this case, we can see that people who were in ticket class 1 has a higher survival rate. And we do the same process. So if we're looking at the sex, how many females survived and how many males survived? And we see that females had a higher survival rate compared to male. And in the other case where we find the number of siblings or spouses in a ship, so people who had pretty much people who had only one sibling or one spouse had a higher survival rate compared to people who had four siblings or spouses had a lower survival rate. So again, it's always important to just understand what the data you're working with, understand which specific part of the data set, or pretty much what features give me more information about the survival rate of the specific class. So it's always important to do that. And of course, I'm just gonna gauge to this. Like, you can look into the facet grid. Basically, Seaborn allows you to plot a histogram allows you to be like, oh, okay, so facet grid actually just takes in the data and tries to find the column survived. And then what it does is that it tries to make a histogram using matplotlib, and it makes age as your independent variable or your x on the x-axis. So in this case, we can see that doing some observations, infants with who were less than 4 years old had a higher survival rate, as you can see right here. If you compare, if you compare your survival equals 0 to survival equal 1, you can see that a lot more infants had a higher survival rate. Passengers who were 80 did survive, which is really good. And you can see that a large number of the people that were in this Titanic were between 15 to 25 years old, and most of them did not survive. It's really cruel, but that's observations we're making here. And again, I'll have you guys just go through all this data set. This will help you just understand like what's going on. In this case, we have like the survival rate between the survival rate dependent on the ticket class you're in. And then you have the survival rate of a female and male, depending on where they embarked. Um, and yeah, so just go through all this. This is just meant for visualizing your data and just understanding your data. But pretty much all the data I gave you, or pretty much what I told you, is just enough to understand what's going on. Now, when you go through all those data sets, you have to understand, okay, so I after making all these observations, what do I need to like take out? What features do I need? What features do I need to keep, and which features do I need to take out? So in this case, when you wrangle your data or you're pre-processing your data, we can see from our observations that we don't really need the ticket class or the cabin number. That's not really important to us. So let's just drop that. And we can also do the same for our test data set. That's not really going to help us at all. And so when we run this code, we can see that we had 891 participants. Well, we had a matrix of 891 by 12. So we had 891 rows, meaning that is the passengers, 891 passengers, and we had 12 different features. But since we took out 2 of those features, now we have a column of whatever the column is, the column size, subtract by 2. So in this case, I had 12 columns before, now I have 10 for the training data. And for the test data, I had 11 columns before, now I have 9 after taking out the ticket and the cabin. So pretty much what I'm doing here is just combining the data after modifying it, taking out the features I don't need. And now for this case, what I did here is create a new feature. So we pretty much just create a new feature by extracting some of the existing data that we currently have. So for dataset and combine, which is basically our training data and our test data, we created a new title, create a new feature called title, and we pretty much extract this. Now I wouldn't say the surname. It's pretty much how people would address you. Is it Mrs., Countess, Dawn, Doctor? It looks for that. It looks for those names. And if we look back in our previous data, you would see that people had Mr., Mrs., Miss, Mrs. So basically, it looks for and then in the name, it looks for a dot right here. And once it finds that dot, then it'll extract that. It'll extract that string and put it in, and then add it into our column data. So right here we have captain, we have Cole, I don't know what that name is. Countess, master. It's kind of funny back in the days people would just address you as master. That especially in the Titanic. They had Mile, Mrs. And so yeah, we have all these names, but pretty much if you don't want to take into account all these like different names and just want to make it simple for yourself, pretty much just iterate through the whole data set using this for loop. Now the for loop just iterates through all the data sets and it iterates all through all the data sets in the combine variable. So gets a data set title, and then it replaces lady, and it replaces all the names that you think are rare. So for example, we have lady, countess, captain, doctor, and it replaces those string names into rare. And for the rest that are important to us, we could replace MLE to miss, Mrs. to miss, and MME to miss. And this is our data by lot. Oh. So yeah, and you can see that the people who are named master, 50% of them survived. For those who are rare, about 34% of them survived, and etc. Now, when you guys deal with data sets, right? One thing you need to also look for is how your data is represented. So basically the data types. So in our data here, actually, let me just create a new column or a new cell. Is this right? Yes. So we have our train data dot head. So name, sex, embarked, and title are all alphabetical, or what we call alphanumeric. Pretty much they're represented by a string, but we don't want that. So in order to actually analyze this data, we need to convert all these string values into ordinal values. So like 1, 2, 3, 4, etc. Because when we train our model, our machine learning model cannot understand the string. It'd be actually really cool if it could understand the string values, but it cannot. It cannot in its raw form. So we have to convert it into numbers, something readable for the model. So that's what we did here. Title mapping. We basically just associate the string name into ordinal values. In this case, 1, 2, 3, 4, and 5. So that's what we did there, and we then again update the data set. We make sure that we iterate through the data set in our combine variable, and for all the data sets that have the value name title, we pretty much map all the values, or all the string values, which is Mr. and Miss, into the ordinal values. And then in this case, we fill in any like null values with 0 if there is any null values. So yeah, that's pretty much what happens. And so yeah, I mean, you guys are getting pretty much the flow. Like you have to understand your data. And this is the same thing right here. Like we have our training data. We don't exactly need the name or the pass energy. That's not really important. So you just get rid of that. And then now you have a different shape for your training data set and your test data set. Just figure out what features are most important for you when you want to train your model. So now going to the next block of code, we have, now we want to make sure that sex, or female male, is actually an ordinal value. So our female will be 1 and our male will be mapped to 0. And so this is what we need to do. Iterate the data set again, look for the sex column, map the female and male values to their respective values, integer values, which is 1 and 0. So you can see here that all of our values that were once string are now are mostly numerical values. And of course, like we want to look into the grid again and see like, all right, so let's see our data. Let's try to find the correlation between like our ticket class and the sex, and you can see that again. You can see that most of the people in class 3 survived compared to class 1 and class 2. Well, you can see in class 3 that not many of the people survived, so that's good. Oh, actually, sorry. What this is actually just describing like the demographic of male and female in their respective ticket classes. So just gives a demographic of how many, for example, how many females were in the P class, in the ticket class 3. And yeah, so pretty much what happens here is I'm pretty much just making these guess ages, and it's not really important to actually just remember it. Basically, it just tries to output some random value. It's not really important. It's just more of like just finding the mean given. Okay, so pretty much we're iterating over the data set sex and the P class in the data set, and we're trying to pretty much use these age values, or these guess ages that we make, to replace any of the ages that were not really known. So that's pretty much what we're doing here. I mean, this block of code, you don't need to really understand pretty much. It's just we're trying to visualize our data, understand our data, what we need to cut out, and what we need to add. So again, we need to like maybe generalize, like, okay, so between this specific age and this specific age, like for example, from 16 years to 32 years old, how many of them survived? And that's also really important to know because I know in general people have a general age gap that they would like to, especially in statistics, like, oh yeah, 16 from age 18 to 21, this is the amount of people who have diabetes, right? In this case, that is basically what we're doing. We're trying to group a specific group of people, given their age range, and see how many people survived. And that's really important because this helps us understand the data a little bit more to find out what exactly do we need to look into for training our model. So again, I'm not going to go into too much. I'm not going to go through all of it. I want you guys to actually just look over it and just understand what each line does. So we created the age band, we created the family size, see how many of them survived, and then for those who were like alone and didn't have who didn't have anyone with them, so pretty much no spouse, no family, we also created that too. But now the other thing that we need now, and of course I'm not gonna go too much, it's just adding more features. Fair band. See, fair band is just like the age band. We want to see how many people survive given given a range of how much money they spent. So in this case, people who spent $31 to 512, actually there is a higher survival rate in that group. It is a lot of code, and this is something you'll see when you work with machine learning models. Like not a single program that you write, it's gonna be like 10 to 20 lines. It's probably gonna be more than 100 if in any case. So now this is when we do the fun stuff, the logistic regression model that we were talking about. Now, like what we did in linear regression, right? We split our data into X train and Y train. So in our X train, we pretty much want to drop our survival probability, which is from 0 to 1. And we want our Y train, or which is our labeled data, to take in that column value. So now when we create our X test, we also want to drop passenger ID because it's really not something we need. So pretty much when you run this code, it basically just outputs the shape and tries to understand what your shape currently is at that moment. Now copy basically, okay, so I know for most of you guys, there's a lot of function here that you need to know about. If you guys want to know a specific function, for this one, this is from NumPy. You can always look at our documentation to see what they've done. Like for example, np.numpy. Basically, it just copies the array, so it doesn't overwrite the current. It doesn't overwrite the current the data that you assigned it to. So it just copies the data or the matrix so that it has its own specific set of data points. But yeah, basically, wait, this is constants. Oh, np.copy. It returns an array copy of the given object. Usually what I do when I do machine learning or like follow examples is if I don't understand a specific part of the function, or if I don't understand a function, I just look it up through the documentation. Now, if you don't exactly know where the function's from, because we have a bunch of libraries, just remember what each library does, and then you can sort of narrow down to which Python libraries I should be looking for. So yeah, I mean, looking at all this, we've gone a long way. We pre-processed all of our data. We found all the details we need. We finally converted all of our string values into numerical values that allows our model to understand the data. Now let's actually apply a logistic regression model. So in this case, what we did here is initiate our logistic regression model from sklearn. Again, just like linear regression, we use a fit function to feed our model with the X train and the Y training data. So it'll just look into the data, feed in all the parameters into the logistic regression model. In this case, going back to our going back to our logistic regression model, it'll just feed in all the x data into the sigmoid logistic function. Our theta values will be calculated, which or our model parameters, and etc. So it'll do all that just for you. You don't have to create like your own logistic regression function. If you do, I encourage you guys to actually implement your own. But to make your life easier, sklearn just does everything for you. And from there, we got our we finally trained our model, and we got 80% accuracy. So that's pretty good. But in general, there are some things you guys need to know. 80% is okay, but what you really want is 99% or 99.99% accuracy. It's actually really hard to achieve 100%. Only humans at this point can only achieve 100%, but machine learning models, they can get close to 99% or 99.9%. That's what we want in general, because we want a good model that can generalize very well to different test data that isn't given the training data set. Now we got 80.36%. It's good. Now, if we look into our YPRED, this will produce a matrix. Your YPRED outputted an array that contains all the prediction values that pretty much all the prediction values that we have. It pretty much outputs the prediction values for all the data sets and for the test dating set. So in this case, we have our where's our X test? So our X test right here is, let's put our X test. So pretty much the model learned that, okay, so this person's in P class 0, sex is 0, age is 2, fare is 0, embarked is 2, title is 1, etc. And it looks through all the data sets, look at the training data set, and the model's like, oh, okay, so this person 0, are their personal ID, which is 0, actually did not survive. That's 0. So if you want to know the length of this, like the length of YPRED is 418, and the length of your X test, or it would be better to get the shape of it, is 400. Wait, X test dot shape. Why is that 2? X test dot. Oh, I see. I put length. That's why. So your X test is 418 by 8. So in this case, our YPRED produced 418 values, all associated to the personal ID. And so we can see that from 0 to 4, so pretty much 0 to 3. Oh, sorry. Yes, so 0 to 3. Remember, the first index is 0. So from 0 to 3, these guys did not survive. But 1 right here, 4 survived. So pretty much this is an okay like model. It was able to output, it was able to predict it with 80% accuracy. And of course, there is a better way. There are better functions that you can use to actually predict, to have a better accuracy. And in that case, let me show you what you can use. In the meantime, does anyone have any questions at the moment? Can you post the slide afterwards? Yes, I will post the slides afterwards. Everyone's Gucci. Okay. I'm telling you guys, machine learning is it's not easy. There's just a lot to learn. And I know cramming all this information is like maybe overwhelming, but if you just look over the code and just have um just look over the code, try and understand it. Maybe um for do your own example with a different data set using the code that we have. It's actually still it's pretty applicable, just being able to um follow this whole process where you collect your data, prepare your data, train your model. All this process is well universal. Um, but yeah, in the meantime, I have these resources for you. Now, I was mentioning earlier that there are different algorithms that you can use to that you can implement that could better the accuracy or lower the accuracy. But that's something for you guys to try. That will be your homework. So there's different types of machine learning algorithms that are pretty important in supervised learning. One is k nearest neighbors. Support vector machines are really big. Decision tree classifiers and random forest classifiers. It's okay if you guys don't know this, but on the right of the figure, I did post some of the functions that you can upload or load into your program and test them out. If you just look into the documentation, it's pretty much they pretty much give you all the documentation you need. But in this case, try it out. Now, if you um, now I mentioned before that mathematics is really important, so I have all these resources for you guys that you guys can check out. Now, Mathematics for Machine Learning is a really good book. It does a great job in explaining the different types of the different types of math that you would encounter in machine learning. So in this case, linear algebra, they pretty much give you a good introduction of linear algebra and how it works. Um, and I'm pretty sure you guys learned system integration. Over here, this is the basic mathematical operation um, that we use, which is just like matrix addition. And they even talk about transpose and matrices and how everything is like ordered or indexed. Um, Another really great book that I also recommend reading. It's called Deep Learning by Ian Goodfellow. Now, when you guys get into deep learning, this book actually does a great job in explaining the math behind deep learning. Um, Now, there's a like right here, applied math. Basically, just giving you all like the specific types of topics you'll encounter. For example, linear algebra, probability, information theory. These are all important. Now, what I recommend you guys do is once you guys do finish a topic or a section in the book, try to practice it. Try to apply it in code. For example, when you work with deep forward neural networks, try to create a neural network from scratch. Um, Basically using Python and NumPy to create a function that feeds all your data into the neural network. Another one of my favorites for understanding probability is actually seeing theory. Now, this is one of my favorites. Like, someone created this really visual website that helps you understand probability. And this would be maybe appeal to most of the people who are visual learners. So, for example, if you want to learn the chance of events happening, flip the coin, um, flip the coin 100 times. All right, so it pretty much if you flip the coin 100% times, 100 times, it'll give you like a probability of your heads being or your coin turning to heads and your coin turning to tails. So after flipping 100 times, it tells you, all right, you have a 56% chance that your coin will be heads and a 44% chance will be tails. These are all really important. Another thing is expectation. Expectation is really important too. It's basically just mean. And variance. This is another. Honestly, like I recommend just looking into this website. Another great book that I recommend you guys read is called Hands-on Machine Learning with Scikit-learn with TensorFlow and Keras. Now we're not using TensorFlow or Keras because one, a lot of people don't use. Okay, a lot of people use Keras and TensorFlows, but ever since PyTorch came in, a lot more researchers have been using PyTorch because one, the API is a lot more stable, and two, Keras and TensorFlow. Well, actually, Keras is good, but TensorFlow, the API is really unstable. But they do have really good content that helps you understand how these algorithms work. So, for example, if you were going to linear regression, right? Oh, not linear regression. Actually, I got all my formulas from this book. It's really really intuitive, and he does a great job in explaining how logistic regression works as well as the formulas. But since we talked about, like, for example, decision trees, um, he gives you a good introduction of how decision trees work, and he has a lot of example code. In this book, he uses sklearn a lot. So I recommend you look into this book, and when you go through this book, try to go back to the Titanic dataset and try to apply these functions or these algorithms. And yeah, so I give you some other resources, and of course, I'll be able to give you guys other resources as well. Usually, I'll post them in the Discord channel. But yeah, so really hope you guys enjoy these resources. We also have a GitHub that we're working on right now, which will give you a better idea, which will give you more resources in the near future. And they're going to be really helpful too when you want to learn PyTorch from scratch. But with all said, that is pretty much all we have for today's workshop. I know that was a lot. That was like a 2-hour workshop, but I really hope you guys found that really helpful and intuitive, and a reason to actually apply machine learning. But when you guys do apply machine learning as electrical engineers, one thing that when you guys get into, let's say, Tesla or Waymo, you'll be able to use machine learning to actually read data from like sensors like LiDAR, cameras, sonic sensors, and etc. And all these machine learning algorithms can be used for guidance, navigation, control applications, such as being able to avoid obstacles. So you're getting all your you're getting all your data from like the sensors, and then your machine learning model tells you, wait, um, there's an obstacle right in front of you. You should stop. Another cool thing that I actually talked about with my colleagues is the SLAM algorithm, which is basically used in autonomous vehicles and SLAM stands for simultaneous localization and mapping. So basically, the car is able to localize itself in the environment as well as map the environment itself so that it could prevent any collisions with anyone, such as like people, cars, and etc. And you can use machine learning to gather all these data points in real time, what we call inference. It gathers all these data points, learns from it, and then it tells the autonomous car, hey, make sure you don't hit this person, or hey, you should brake right now. So this is how machine learning is used, and this is going to appeal more to you guys compared to just analyzing data sets or a data set that like maybe tries to predict the probability of someone dying in Titanic, or the probability that someone in the age of 15 will enjoy donuts. So yeah, these are things that you guys should take a look into. Look into autonomous cars. Look into how machine learning is used in autonomous systems. See how machine learning is used in speech recognition. Speech recognition is a really nice topic too, especially for those who are specializing in digital signal processing. That's really nice. Yeah, so just check out all those topics. They're really awesome. Recommend you guys take a look into it before we go and dive into neural networks. Yeah. With that said, does anyone have any questions or comments?
Yes, it was a really nice workshop. Thank you, first of all.
Oh yeah, no
And
worries. Thank you.
secondly, what are you going to discuss next week?
Yeah, so next week we're actually going to talk about more advanced techniques, which is neural networks. For those who, so neural networks is basically, okay, let me give you a breakdown. Neural networks are not machine learning like the classical methods we have been using, such as logistic regression, linear regression. All those models are okay if we have a small data set. But let's say you have a data set that contains millions of images, right? Like, okay, machine learning model will probably understand, like, be able to classify those images. But imagine how much time it's going to take to actually iterate through the whole data set. It's probably going to take you a year, especially if you don't have like a good hardware hardware specs, it's going to take you a year um, to just train the model. So neural networks actually does a better job in not only speeding up the process, but neural networks does a great job um, in analyzing your data set a lot more efficiently than classical machine learning methods. So a neural network that you guys may have seen before, a classic neural network is this one right here. So pretty much a neural network is like, there's different types of neural networks, but this is just a simple neural network, which we call a multi-layer perceptron. Basically, it has an input layer, which takes in the data set. It has a hidden layers, which is basically just the process where it learns from the data set that you input it, and then it tries to update the model parameters, which is the theta. But in neural networks, we usually in general we refer it to as W, which stands for weights. And then we have an output layer. So for a really nice example would be image classification. So instead of using actually image classification uses logistic regression. It uses the sigmoid function. So let's say you have an input layer and you have let's say you have a 20 by 20 image. First, the program actually has to um, it has to make the image or the data or the matrix actually 400 by 1 because it's hard to actually read an image. It's really hard to read a matrix. If you fed the model with a matrix, it's going to be really hard. You'll pretty much get an error. So it has to what we call flatten the matrix into a one-dimensional or a vector. So pretty much 784 by 1. Oh, sorry, 400 by 1. Fit an input layer, and then each pixel or each value in the matrix will be associated with a weight value. And what the hidden layers does is it actually tries to learn from these hidden layers. Learns from the weights, tries to update the weights. And then once we have all the weights and we learned pretty much all of it, then it'll go into your output. Now, if we're using a sigmoid function, our output will basically just be one node. So once it feeds in all the data into the sigmoid function, and we want to classify like a dog and a cat, then it'll output it'll output a probability of 0 or 1 to specify that the dog is a dog to specify if the image is a dog or a cat. Another example would be if you're trying to identify a specific number on the image. It's a classic example created by LeCun, really popular researcher. He's a director of machine learning for Facebook now. But pretty much, if you want to identify if the image is a 1 or a 2, 3, 4, 5, 6, 7, 8, or 9, then pretty much you would do the same thing. You flatten your matrix, feed it through the hidden layers. Then your output, which is one node, will output 9 different probabilities, each specifying the value that the probability of this image is 0 or 1. And whatever the highest probability is, the machine learning model will tell the program, all right, so this image is a 9. And we'll actually go through that example. The classic example I just mentioned, we'll actually go through that. It's commonly used in a lot of tutorials and etc. But it'll be a good practice to get you started with PyTorch.
Great. Thank you.
Yeah, no problem. Does anyone else have any other questions? All right. So if no one else has any questions, then that's pretty much all for today's workshop. Again, I will send the PowerPoint slide in the Discord channel, and we'll try to upload the videos on YouTube. So just give us a little bit more time. We're trying to figure out like what the problem is. But yeah, so other than that, guys, I hope to see you guys next Friday. And if you guys have any questions or looking to maybe do a project or want to do some project experience, just always let us know in the Discord channel. But yeah, other than that, guys, enjoy the rest of your day.
Thanks. And what is the name of the channel? on YouTube?
Oh, yes, the server, right? Let me. Wait, are you in our server, by the way?
I am, but just logged in with another email.
Oh yeah, so the channel so usually I would send all the resources in like the resources channel, in our Discord server.
Wait, I just have like I got your link from the IEEE Discord server, right?
Mm-hmm. Oh, sorry. This is the one we're talking about. It's a machine learning server. Let me see if I can send it.